Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today is going to take a look at the C++ standard template library class called Map, and possibly Multimap as well. And then we're going to look at a slightly higher level for a couple minutes here with the underlying principle of the map and the multimap, which is the associative array. So the reason why I'm kind of combining all of these topics, normally I have 2 or 3 different videos related to these kind of things, is because we've kind of already covered it. This is just a slightly different, or slightly more advanced version of a binary tree. And so an associative array, what does it say? It's otherwise known as a dictionary. Python calls it a dictionary, and I don't know enough about Python at this moment to tell you if it's 100% the same, because I've used them. I just don't know the similarities and the complete differences between the 2 data structures in the 2 languages. So I'm sure there are some slight differences when it comes to that, especially syntax, of course, because the languages are so different. So dictionary, associative container, associative array, map, there's different terms for this topic. And so, as you might expect, then you'll find this information in various places. And so what I was describing here is when we were dealing with the binary tree / set idea, you could see here in the graphic down to lower left here that we have basically a binary tree. If you just took the number values just by themselves and not worry about the strings that are attached to it, like the 4 and the word 4, you could see that this is a balanced binary tree, because for every node in my set here, or in my binary tree, a value that is less than it is to my left, and a value that is greater than it is to the right. And it applies every step along the way. Every value over here is less than 4. Every value here is greater than 4. Every value here is greater than 2, less than 2, greater than 2, less than 6, greater than 6. It's balanced. It's a complete binary tree. And so the only true difference when it comes down to it, I mean, there's a ton of difference when it comes to the functionality and the syntax of everything, is that now, on top of having a key value, instead of just being a set, like an element, we call that a key value. And then now we associate that, that's why it's associative, we associate that with a data type that can also work with it, in this case, the string. If you give me an integer value, I will give you the string representation of that number, at least for the numbers 1 through 7. So you say 6, and I will give you the phrase SIX. You give me 3, I'll give you THREE. I'll give you the string value of whatever it is that, of the integer value that you tell me. And so everything comes in pairs. So there's 2 data types associated with an associative array. There's the key type, which is one type, and then there's the value type, which can be the same, but it most likely is something completely different. So like I'm using a map in one of my game courses for keeping track of texture data, so I'm not duplicating all these massively large sprites and graphics inside my games. So I have a string data type as the key. Get me the wall sprite, and then I will get you a pointer to this large data structure that holds the actual data for the PNG image that's sitting in my game. So it's just various different types. So T-type, U-type, if you want to think of it. We're not used to that. This is our first time passing along multiple types to a collection or to a function, or you name it here. So obviously, we've already covered the basics of this, so you can go back to the binary tree videos if you need to, because again, all of those details are covered much better than I'm going to cover here, because they're just variations of a theme here. So when we're discussing associated operations that we need to perform on this data structure, I mean, this is how many data structures? We know the basics, right? We need to be able to add something to this collection. And in this case, again, it's a pair of data. It's a key, it's a value. So like this 4 versus 4. And for another example, be like if you had a listing of cities and their populations. Like you would have Chicago. It would have the city itself has about 3.3 million. I don't know what it is. I'm not going to correct myself if I'm wrong, because that number fluctuates greatly. String in, excuse me, string in, integer out when it comes to that collection of data. So let's see, what else does it say here? Add a pair to the collection, add an element to my collection, remove, modify. and then find. I mean, we've already we've definitely covered this in so many different data structures because that's so basic to what we need to do with any collection is to find data inside of it, add data, move data, change it, and delete it. I mean, at the very core, that's all there is to a lot of these data structures. And so the rule here for the map, so like an associative array, is that each possible key appears at most one time inside of the collection. So the way we're going to set this up, just like a set can't have multiple, there can't be 2 4s in a set. Like when it comes to values, there can't be the word Chicago in there twice, or there can't be a 4 in here twice that points out to different places, that points out to different values. So one key, there can either be 0 keys or 1 key per key, like per key value inside of this data structure. So that's as far as I wanted to go with the Wikipedia definition of things. And so how long are we? 6 minutes into the talk here. So now it's just, and we're not going to be doing anything low level. We're not going to generate our own for this data structure. We're just going to use the standard template library. That's why, again, I'm combining everything into one video. So now, what do we get as a benefit? What are the benefits? What are the detractions or whatever of using the map structure? Because at least in C++, the map is the associative array. So it says it stores unique keys and that too in sorted order, again, because it's most likely setting it up as a balanced binary tree. I've never looked into the actual implementation details, the rules for implementing this in the C++ language. So it might be a requirement, but it might be just a recommendation. You'd have to look into the details. The map is an associative array, and it says here there's only one unique key per data type here, and it's according to its sorted criteria. As keys are sorted, the searching element in the map through key is very fast because it's logarithmic time. Again, it's a binary search, so it only takes log base 2 of the size of my search to either find the data inside of there or resolve down to the fact that it's not located in here. And let's see, in the map there will only be one value attached with every key. So you can't, that's the whole thing. One key can, there's one key value, but that one key value only points to one value. And so one key to one value. And so the multi-map will show an example. The final example here is basically a graph data structure. If you're familiar with graphs, we'll go into that in detail in a little bit here too. So let's see, is there anything else here? And there's the benefits. Is there anything that talks about the detriments of it? Nope, nothing here. So let's just talk about all the good stuff, right? So that is the basic good stuff. And so now we can go ahead, and I'll try to implement this in C++, this kind of data structure here, just to show you, at least as a first example, how to get a map structure going. And so let's do that now. Here is a Visual Studio Hello World kind of deal going on here. I included probably what I'm going to need, maybe a little bit more. Here is my CPP reference. I'm going to say this is a good website again to get this information. And again, I really highly recommend this guy right here, Jasudis Nikolai. Oh goodness, there was my Nikolai Jasudis, 2nd edition, 2011. There might be another one coming out, 3rd edition coming out soon. Sorry about the green screen issue there. Woo, that's what autofocusing does for you sometimes. And those are my resources. Section 7.8 out of the book, again, is a great resource, but so is cppreference.com, and so is c++.com, and a few other websites, of course. This information is readily available. These things are no secrets anymore. So we discussed the map is an associative container that contains key value pairs. And so, like, notice this, there's a lot going on here. Notice we're going to have to use this thing called a pair, which it sounds complicated, but I mean, it's basically a very special two-elemental vector, if you want to think about it, because there's a t value for the key, and then there's another value, like a u value for the value part of the key value pair. And so does it show us this here? Yep. So it's just set class T1, class T2 struct pair. That's all there is to it. And it's templated in its classes, and it's public stuff. So there's a first and a second. These are the member objects that we can access. So for any pair, the first is the key and the second is the value as we go into doing this kind of thing. And so just coming back here, so this is pretty instrumental here. We have to use this to make this thing work. So as usual here, let's take a look at all the constructors that I can do to set up a basic map structure. And remember again, I'm trying to set up a string, or int string key value pair relationship between the number versus the way it's spelled out in English. So std map, and so now you know, oh my god, it's all complicated, but now I'll need string, I guess. Here I am, need string here, so I need to say, okay, give me an int, and I will give you a string. And so that's the data type here, comma separated. 2 parameters when it comes to this thing, and then this is the basic. And I say they just call this numbers, or just just call it numbers. So this sets up your basic default empty map. And so just to kind of come around, all the other things you can do, of course, like how do I insert? Oh boy, right? Initialization list. It gets a little choppy here. Let me just bring this down a notch and see, because we need to use this pair idea, because that's how everything kind of gets put in, because it really is just basically like a special class that gets jammed in instead of like an int or whatever the t type is. It's basically putting the t and the u together into that memory location. It's like a fancy structure. So let's see. And so what I can do here, how do I make this work? So std : pair. I think I can do it this way. And I don't think I need, sometimes you do and sometimes you don't when it comes to what do I need to do to make this work. But what if I put a 1 and then I put an ONE like this? Let's just see what happens. Close the curly brace off and see what it says. And it says, nope, argument list. Okay, so for this case, it does want me to do this. And this is where, whoop, bring it down a few notches. So there we go. Does that work? Let's build just to make sure. And it says, what did it say? Rebuild all successful. So yes, this is a much more complicated way of setting things up, because I need to set everything up in a pair structure, 1, 1. And so you could imagine then if I wanted to keep on going, fast forward here at this point, I guess, to 3, 4, 5, 6, 7. Just promised you I would do the exact same thing. Oops, come on, IntelliSense. Hate the IntelliSense. Sometimes it helps out, but sometimes not so good. Okay, so here we go. So maybe to make this a little easier, sometimes I like to do this just to, because it just makes things a little easier. So 1, 2, 3, 4, 5, 6, 7. Throw the comma in there. Let's see. How well can I spell when I'm being put on the spot here? 3. As you know by now, probably not well. 5, 6, and 7. So that uses the initializer list idea that we've done for every other data type. It's more complicated because the element, instead of it being just t or just u, it's the combination of the two put into a pair. Oh, I still have my data type. I don't need that anymore. So let's see. Did it rebuild successful? Good. All right, so that sets up that with the initializer list. And then, as we've done before, when it comes to using a copy constructor, again, a huge difference between these two lines of code again, right? Or if I just say p equals numbers, or something like that. And again, because p is being constructed here on the spot at this moment in time, it uses the copy constructor function to do the work of taking all the values, the key value pairs inside of here, creating completely new, brand new elements and putting them inside of this p structure, this p collection. So that uses the copy constructor, and this, because p and numbers at this line of code here, they both are perfectly alive and well. They're both constructed and working inside of our program. This uses the copy assignment operator instead of the copy constructor. Again, to the compiler, two completely separate ideas, but to us conceptually, it ends up doing the exact same thing. We're just setting everything that's inside of numbers and setting it equal to everything that's inside of here. And so that's about that. And if you wanted to, then you could also set up, let's say, using the idea of the iterators. So there we go. So I can say start from numbers.begin and numbers.end and iterate through this data structure and use that as the copy mechanism to create the P data structure. So I think that covers, that's this idea here, copy constructor, normal, empty, and that's about it when it comes to this. Yeah, we're not going to follow any of the others. So that handles that when it comes to constructors and this operator. So again, Destructor, the Destructor, of course, when this map structure gets destroyed, there's a ton of dynamically allocated memory sitting under the hood here. But the Destructor will take care of that for us automatically. We do not have to worry about how the map does its job. We just use the map and then it will clean up when it needs to, which is very nice. Oh, there's an at function now. Okay, so let's move on to more of the functionality as we go to this, because we already have this. So how would we, so how can we do things with this? So earlier I was discussing the idea of, hey, for Chicago, tell me what the population is. And so, and that's exactly what I can do. Like, how do I access this? You can kind of do this like an array notation. And so here, if I wanted to, I could do cout, and I could say, just kind of comparing the same thing, I want to say, okay, numbers, give me whatever 1 is. Print that out. And it prints me out a 1. Isn't that pretty cool? I mean, so that's how you can actually go ahead and do things that way. And but the fun thing here is what happens if I try for 8? What will it print? Actually, it doesn't. You think it doesn't print anything, right? You're like, oh, okay, it just prints nothing. But what really happens, this is the interesting part here, is if I do numbers 8, I go, oh my goodness, hold on, let me put the breakpoint before I try to actually access this thing. So you're like, okay, numbers has 7 elements in it. There's my 1, 2, 3, 4, 5, 6, 7, as you can see, and you can see the key value pairs. 1 goes to 1 and so forth and so on. You can see that. But now what happens if I try to access this? So what comes back is the empty string, but look what it did. The numbers is now 8 sized, and it filled in the 8 with an empty string. And forgive me, I don't understand why this occurs in the map data structure. If someone would be willing to just maybe put a 1 or 2 sentence demonstration of why this is the way it is. But this is what happens if you try to access the data that doesn't exist inside of your map structure. If you can't find the key, we'll add one for you right on the spot, and we'll fill it in with default data, which is default meaning what is the null template. Like if it was a value, an integer value, it would be 0. In this case, the null idea, the 0 idea, is an empty string. And so I'm curious, because I haven't even, it's been a while, and this at function, what happens if I try this? Does it crash on me? What does it do? And so yes, it will crash out of range at memory location this, because I tried to access something that didn't exist. So that's what I think of when I think of especially when I think of vectors and things, this and that. When I think of the square bracket operator, the array access operator versus the at function, the square brackets array notation doesn't do any checks. It just figures out the math and just goes and gets something. But the at function will actually do some range checking and throw an exception if something goes wrong, because that's exactly what happened here. The value of ESP was not problem. Oh my goodness, blah, blah, blah. ESP screams out that it's a memory problem with my call stack. I don't know if that's necessarily the case, but just to say, yes, in this case, if you're using the at function, you're usually tying it to a try-catch block. And let's just see what happens. Let me just put a breakpoint in here. At least it'll, so the exception won't happen anymore. So it came around nothing printed, but then numbers is still 7 sized. Because I tried to access it, but it crashed on me, so it didn't add that empty string to my map structure. I feel like it corrupts it, right? Like if I did it the other way, I would be corrupting it. So just fair warning there. Okay, so moving on. Oops, I don't know what I just did. So moving on. to other things. You can have, I'm not even, this time we've done this so many times, empty versus size. And as you can imagine, empty just checks to see if the map structure is 0 sized or not. And size will return an unsigned int, a size t data type that indicates how many elements have been, how many key value pairs have been jammed in to my data structure. Okay, so let's move on and talk about iterators. So remember, the keys are stored in sorted order by whatever that sorting mechanism is. In our case, it's sorted low to high. So now that we're discussing that, I can go ahead and use a range-based for loop, or we're talking iterators, so I can just say, oh my goodness, how complicated this gets. And say, okay, let me start out with an iterator. And I just want to print stuff out, so I'll do a const iterator. And so I'll just say iter, and that equals numbers.cbegin. So notice over here there are 8 different iterators, 4 different types. Same as always. There's a forward leaning one, a reverse leaning one, and then there's also when it comes to const and non-const. So that's why you have 4. So you ask yourself 2 questions and you figure out which one you want to use from there. Am I going in reverse order or not, or am I going in const or not? So I'm doing a const iterator going forward. Put my while loop in here, while iter does not equal numbers.end. Okay, so this is what do I see out here? So again, in most other things, you'd be like, well, it only gives me the value, because when I went to print out, when I said, oh, give me element 6 or something like that, it would print out the word 6. But when I get this as an iterator, I can see now I can say star iter, and I go star iter dot. Nope, that doesn't do it, but star iter arrow, and there we go. And so I can actually go ahead and get me what I need. And I'm saying I'll print out the key, and then I'll print a space, and then I'll actually print out the value associated with it before I go on to the next line. And so both of these kind of throw up a fit because of the way the order of operations work on this thing. So does that fix it? No, that does not fix it. So sometimes like we all kind of get there a little bit with the way pointer notation and all this goes. And so I can't use star dot, but I can use, can I use iter dot? Nope, but I can use iter arrow. And so I just overthought myself into thinking, how do I dereference this thing? And since this, the arrow operator is star iter dot. That's what that is. And so just to say both ways get you to the same pot, this is just a shorthand way of doing star iter in parentheses because of the order of operations, and then the dot to get me to the second part. So this should print out all the oops. I was even going to say to myself, don't forget to do the iteration. Oh yeah, if I just leave it like this, just to show you, since I laughed, and it's just printing 1 1 1 1 1 1 because I'm never changing the status of my iterator. I think I've done this in every single video because I get ahead of myself as always, and I just don't do it that way. So there we go. So there's 1 2 3 4 5 6 and 7 when it comes to every element in my map, and it gives me both the key and the value for those situations. Oops, and wow, I'm surprised this actually worked. cbegin, I should be using cend. You should 100% be using the correct begin and end, cbegin, cend, or just plain old begin and end, or rbegin and rend, or crbegin or crend, because in this case it worked out okay, but there's no guarantee. And so how about const reverse iterator is crbegin, and as long as iter does not equal crend, I can run this. Notice that those things didn't work out, and now just by changing a few little things there, everything's coming back at me in reverse order. And again, the plus plus, it's weird because we're going reverse, but if I'm going in reverse, plus plus is actually just going ahead in the direction that I'm facing, so I don't have to change any of that other code. So crbegin, crend uses the const reverse iterator. So that is this one here. It returns a reverse iterator with constant or non-constant. Okay, so we're going to need to use pointers for some of these other things, so let's take a look. Let's just keep on going with our functionality here, and just, my goodness, this one's got some fun with it, right? So let's just keep on. Do I need to worry about anything else here? Nope. Let's move on to the modifiers. Clear will do exactly what you think it would do. So if I do numbers.clear, it will clear the thing out, and I'll print nothing because there's no longer any elements in here. And again, as everything else, if you have pointers to dynamic memory and you want to get rid of them, that's your responsibility. All this thing does is just destroy the pure data sitting in the data structure. Everything that it's pointing to, if it is pointing to things, are not destroyed. So you got to watch out for that. So now insert. So like, how would I insert an 8 or a 9 here? Numbers.insert, and you've already seen it here. Let me just steal this. This is essentially what we're doing. We're inserting a pair, and I'm going to say give me 8 and give me 8. And again, if I try, let's just to show, if I try to do this twice, it'll only come up once. And since I'm doing this in reverse order still, it comes up first, not last. So there's my 8, and since this is map and not multi-map, this thing comes up legitimately as just one element, number 8, that points to the word 8. Okay, so there, insert. So now finding something. So again, this is a binary tree. This is a set structure under its hood, just a repurposed one. So how can I go ahead and do this? And so it'll return iterator. The find function returns an iterator. Iterator. And I'll just call it I this time, and it's equal to, is it not happy? Why is it not happy? But just regular iterator, and it's equal to numbers.find, and then inside of here, all you do is give it the key value. I know I have key value pair. I hate that. Anyway, what is it not happy about? Oh, std pair. I meant std map. There we go. So give me a map int string iterator. And then so if I want to print this out, or if it found it, if I does not equal numbers.end. So in this case, it's searching. I didn't give it any iterators to give, like a certain region of the map to search for this key value pair. So basically, if it's the whole data structure and it can't find it, it's going to return end iterator. And so in this case, so I can just kind of get rid of this nonsense over here. And put it in, oops, jam it in. Where did it go? Put it in over here. And since I did all this, maybe I won't change the word I, I'll just change it to iter, just so I can save myself that typing. Okay, so now only if the 4 can be found will it print the 4, and there it does, it prints 4 and 4. But if it can't find it, so if it looks up 14, it won't print anything at all, because it comes up as the same iterator as end. And again, end is one past the last element. So begin starts inside of the collection, but end always is one past the end. And that's consistent across all of the standard template library stuff. Okay, so that covers the find function. And then we've kind of discussed this. Let's talk about lower bound, upper bound one more time. Okay, so here's a little demonstration. I've changed things up a little bit. I only have 4 elements now in here, 4 key value pairs, 2, 4, 6, 8 with their appropriate string representations. And now here's a completely different way of going ahead and printing out every element in my map. And so I can use this lower bound and upper bound function to make this work. So I start off, the lower bound function says, it returns an iterator to an element not less than the given key, which means greater than or equal to. So what is greater than or equal to 2 in this case? It's the 2. So it starts with the 2, and the upper bound says returns an iterator greater than the given key. So what does that mean? If 8 is the last element, what does that mean? Let's put a breakpoint in and find out. So that means my low is pointing to 2, because not less than means greater than or equal to. I wish they would just say that, just be plain English about it. But high, what comes after 8 is the end iterator, which is interesting, right? So the end iterator technically is greater than any other value stored that could be stored inside of this thing, because it's one past It's one element past the 8. And so, of course, since I started with the 2 and I have end, it will print 2, 4, 6, and 8. And so, just real quick here, just to show them, if I reverse this, make sure I do it right this time and talk about it, what should I get? If I use upper bound with 2, upper bound says, what is the first element greater than the given key? What is the first element greater than 2, but it's the 4? And the lower bound says, not less than, which means greater than or equal to, right? So what is the lower bound of 8? And that actually should be the 8, right, in this case, but maybe not. Let's see. Low gives me 4, high gives me 8. But now you're like, well, what does it print then? You're like, this is where things get freaky, right? Because the way begin and end, begin is always online with where you're starting, but end is always offset by 1. And so it's a little freaky because you're like, it is an 8, but it doesn't print it. It prints the 4 and the 6. So because I print out and then I increment my iterator, and then when I come back around, the low is pointing to 8 and the high is pointing to 8. So even though 8 is technically part of the iterator list, it never prints it out because the loop kicks me out, because that is essentially my end when it comes to this. I'm not supposed to be printing that out. It's basically my end iterator for this subsection that I'm trying to do. So that's why it prints just the 4 and just the 6 in this kind of situation. Okay, so I want to do one more example here, something you might see in one of my homework assignments or maybe my extra credit assignment, depending on the term and depending on whatnot. We'll come back to, let's do the Yahtzee problem one more time and see, because we've already done how to use a set to kind of figure out Yahtzee from 4 of a kind and that kind of stuff. So let's talk about how we can at least get the values into here. And then we'll have, we'll have one more example with a multi-map as well. Okay, so here is some kind of code that I could write that uses a vector and a map. And as you can see, we have some results here. So I'm setting up a map of int. And so what I'm trying to do is I'm just trying to figure out for every die value, how many dice have been rolled of that exact value. And so the int is the die value, and the other int then is the number of times, the number of occurrences of that die being rolled. And so that's my map structure. And here's just a plain old vector. 1, 2, 3, 2, 1. Those are the 5 dice in my Yahtzee game that are sitting in front of me. And so what I can do here, this is pretty interesting, right? So a minute ago I was telling you how it's weird that I can just initialize an item out of nowhere without crashing my computer, right? Without throwing an exception or doing anything wrong. But I can tell you for every integer in my vector, go ahead and add it to my map. And so I can do dice I. Remember, if it doesn't exist, it turns it into, it actually makes it exist inside of my collection and sets it to, basically the default value, and default value of an integer is 0. So it will set up, if like for this case, the 1 will set up and you say, okay, now there's a key of 1 with a value of 0, and then let's increment that. And so now that time, key 1 gets value 1, and key 2 gets value 1, and key 3 gets value 1, and then I'm no longer generating anything new because the 2 and the 1 already exist, so I'm already adding on to what I already have. So this is just a fancy way of printing out everything inside of my collection, and you can see here it is. There's 2 1s, 2 2s, and 1 3. So this is a good way of, like using the map structure in order to do something pretty cool like this. And now what do you do with it? I don't know, but it's just to say between the set and the map, now you can go to town on using those data structures together to try to figure out exactly what we, in this case, what do I have here? I have 2 pair. I have 2 pair because I have a 2 of a kind, a 2 of a kind, and a 1. What do I do with that? Information, I don't know, but you have that accessible to you. Okay, one more example, a little more complicated example, and we're going to move on to the idea of a multi-map. Okay, so here is the idea of a multi-map, and so the only big difference between a map and a multi-map is that I'm allowed to have the same key multiple times. So one thing you notice here, and so I'm going to have keys go to different values. So without even discussing what I'm talking about here, I say, okay, I have a character pair. And so I'm going to insert into this multi-map. An A goes to B, or an A goes to C, and so forth and so on. As you see here, all these little linkages. And so what this is, I'm actually setting up a graph structure. So, this is something, if you haven't covered it here, you will cover, especially if the Lewis program and in your future studies. Like graphs are a big deal. Video games, how do I know the shortest path between 2 points? how could I set something up to actually determine that and be sure that the data, the path that I generate is the correct shortest path. And so I'll spare you watching me put this in. You already see my giant, crazy, wonderful artwork. So let me fill in all this so we can discuss what this code does. It's even more than you were probably hoping. So here it is. I took all the linkages and I drew arrows between them. A goes to B, A goes to C, and so forth and so on. I double checked this. I'm pretty certain I did everything right. And so what this code does, sets up a multimap in this way. And so under the hood, there's all of these links with all these different all these different paths. And so my code asks me enter a starting node, enter an ending node, and it will figure out between those 2 points all the possible paths that you could go down without duplications. Because like between, if I wanted to go from A to C, I could go from A to B to 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 A to B. It could get lost in there. And so that's not what we want here. We're just all unique paths, the simplest unique paths to get from wherever to wherever. And so it prints out all the valid paths, and then it tells you the shortest path of all of them, or a shortest path. If there's multiple shortest paths, it just gives you one of them. So just coming back here, this is hard to, let me see if I can do that. Hold on 1 second here. 1 second. I can't do all of it at one time. Anyway, so if I wanted to go from A to G, it tells me, okay, so how can I get there? It tells me I can go from A to B to C to D to G. That's legit. That's 5 steps there, or five total nodes, 4 steps, I suppose. I can go from A to B to E to G. I can go from A to C to D to G. So there's multiple different ways, and if you find a different one, because F is a dead end, so anything goes to F is a dead end. A to B to E to G, yeah, I think I already said that one. Let's see, A to C, and A to C goes to D. Yep, so I think I've covered those. I'm pretty sure those are the only ways that are covered. And so it takes care of this. So like, how do I get, what happens if I try something one more time? I say I want to go from A to H, but it can't find anything because it's all one-sided, right? Like I can only go from A to B, from B to E. There's, like H is only out. There's nothing that goes into H. So I could go from H to pretty much, well, I don't know, can I go from H to anything? That's a big question, right? Do we really care? But go from H to A? Yep, there's one way to make it work. I can go from H to D, D to G, G to B, B to A, and I can make it work. And that's the only path, thus it's the shortest path. And so you can only make this work with a multimap, because otherwise you can only have one link to one place, and legitimately all you have then is like a linked list, and it's not very exciting because it's like, well, can I get from point A to point B? And like, as long as you're further up the chain than I am, yep, the answer is yes. There's no doubt. So in this case, this is pretty cool. So the code, as much as it seems pretty complicated, is not so bad at all, I would say. Let's see. It's been a while. It's been 5 or 6 months since I've looked at it. So what have I got going for me? I'm calling this get all paths from. And so I've set up a multi-map already here. I have a reference to the map and the begin and end. And essentially, it's just using Dijkstra's algorithm. I'm not going to go into much detail outside of just talking about it kind of briefly here, and just saying, okay, so if I'm going to start with A as my starting position, I'm going to put that onto, let's see, do I actually put that onto the mid? Let's see, begin, end. But I'm saying, like, so what's happening here is I have my start position, I have my end position, and then also I maintain everything that every node I've been in the process of trying. And this is a recursive algorithm, right? This is get path from here. This is the function. This is the private facing function, and it calls itself. So I'm not going to melt anybody's brain, in myself included, when it comes to discussing this. But it's all recursive, and for step, it basically says, okay, I'm at A. Find out all the different ways I could go. Remember the Sudoku problem I had you guys do? Remember the N queens problem? It's the same kind of deal, where you're like, oh, okay, I have A. I have 2 ways I could go. I could go to C, and then I would continue on to do everything C could do. But if C fails on me, or like in this case, if I go from A to B, then shoot, what can I go for? I don't know. But if I go to A to B, and then I'm like, okay, I visited A because I started there and I visited B. And B's like, well, let's go to A. And then the next step you go in the next, you're like, well, I've already been there. So just like the Queen's problem, we're like, well, there's nothing left I can do because that's not a solution because I've already been there. So like, and it's already been part of the path I'm on. So you avoid all of that and then you resolve back. So now you try the other ways around. So again, just like the n-queens problem, just like a Sudoku problem, it kind of only pushes its way forward when it can and then reverts its way back. So all those possibilities that will end up being false instead of brute forcing just immediately fall away and I don't have to process that. And so in the process of all of these recursions and all of these different paths, trying all the different recursions and all the different paths out, it figures out which ones get me to the end goal, because that's the end. Once you get me to the end, then I can revert back and say, yep, put that on the list, put that on the vector. Where is my vector of things here? Or where is my vector? Yeah, it returns a vector of strings because it adds the path. Again, don't worry about the details. It adds that path once it figures out that, yep, I have hit the end. I've hit the end condition, so I don't need to recurse anymore. I can fall back now because I found a solution to the problem. And as you saw, there can be multiple. But usually what happens is the goal is to find the shortest path. You generally don't always want to find all paths and then pick the shortest one, or just to pick the shortest one. If I could guarantee that the first one I found was the shortest one, I wouldn't have to do any more work. But this exhaustively searches. So from a gaming standpoint, this would probably be good if I had it gives me 3 or 4 or 5 different paths, and then I can determine from this which is the best, which is the worst. Like if the AI is like perfect AI, I would pick the best. If I'm trying to get to a player, pick the best route. But maybe the player, or maybe I want the computer to be, less than 100% challenging, and I could have it pick one of the lesser options. So instead of coming right at you as fast as it can maybe take a detour or something. So it's doing something other than just kicking the crap out of you and just locking onto you dead. So there's a lot going on. This is AI. This is machine learning. This is the beginnings of those fields when it comes to trying to figure out how to program a computer to determine, how to think, right? So because it just feels like it's thinking, but it's just following a very basic algorithm to get itself from point A to point B. Okay, so that's all I wanted to talk about in this video. So thanks for putting up with me as always. If there's any questions, swardb@cod.edu is a great way to get a hold of me. Comments here on YouTube also. Let's see, anything? I don't think there's anything else to talk about with the map. So thanks for putting up and have a good day. See you guys around. Thank you. Bye.